Okay, so let's keep talking about this disease evolution or evolution of disease. And our primary focus here is HIV, but this is done with all sorts of different diseases, especially viral diseases, because we can look at the molecular signature, the molecular information, and use that to learn the history of the disease. And again, the idea is if we understand the history of it, gives us better chance to fight it and block what it is and what it may do in the future. So we talked a little bit about HIV. Started as an SIV strain and then made this evolutionary jump in transmission to humans, leading to HIV in people. So here is the phylogenetic tree of SIV and HIV, looking at the different versions or variations that are out there. Now, where does this become useful? How do we use this in today's world? Well, definitely COVID-19. There's a lot of research into the molecular structure of that, understanding where it came from to, again, prevent, hopefully, future outbreaks of similar versions. It is a coronavirus. There's all sorts of coronaviruses out there, but this one transmits much easier and has a much higher lethality rate. But with HIV, here's just a couple examples of how this is used or has been used, how classification and systematics has been used to study HIV. All right, this is like a Jerry Springer episode here. A dentist tried to kill his girlfriend by infecting her with HIV. So she becomes HIV positive, and it gets traced back to a patient that the dentist had seen. So the dentist somehow collected HIV from one of his patients and then infected his girlfriend with it. Doesn't make sense, not the smartest, brightest bulb, but hey, people do weird things. But what we can see is the way they connected this, scientists looked at the molecular structure of the HIV in the victim, the woman, and then also looked at the HIV variation or strain in the patient and found that they are related. It was then able to be determined that the dentist, infected her by taking the HIV from his patient. Okay, so again, just a weird scenario, but classification helped solve that one. One that you may have more or might be more relevant. Those of you who know Charlie Sheen, back in 2015, he announced he still is, HIV positive. His former fiance or ex-fiance sued him for not disclosing his HIV status. So for those not familiar with Scottine Ross, her acting name is Brett Rossi. She is a actress in adult films. So if she comes up HIV positive, she could have a lawsuit against Charlie Sheen saying he gave me HIV. The way they would prove it, they would look at her strain of HIV, compare it to his strain of HIV. Possibly she would have a legal case or legal support on her side. Potential is if she picked up HIV, she could have picked it up from who knows who within her line of work, but the molecular information and systematics would be able to trace back where she got that HIV from. So lots of uses for systematics and classification. All right, now let's wrap this up with looking at kind of the big picture of classification and how we use it in science. Hopefully a lot of this is familiar and it's a review, so I'm going to kind of go through it fairly quickly, but definitely make sure you are familiar and comfortable with classification and the current system of taxonomy. Currently, we're using what's known as the binomial nomenclature system. Carol Linnaeus, this is the founder of the system. So Linnaeus, make sure I spell that right. Linnaeus developed the Linnaean system of classification based on just physical resemblance. Do you look like this? Do you have these parts and features? Well, then you're related. So when he drilled it all the way down and created names, the first part of a species scientific name is the genus. The second part is known as the specific epithet. We often say species. So Homo is the genus, sapiens is the species or specific epithet. When you see a name in italics, or a word in italics that you probably can't understand or read or pronounce because it's in Italian, that should key you on the fact that that is a scientific name of that species. If you're handwriting it, underline the scientific name. One line under genus, a second line under species. If you're word processing, computer, texting, whatever, hit the italics key. You need to be very conscious of learning scientific names of species to become more familiar with them. Because if I said, right now, I want everybody to imagine a bear. There's dozens of examples. Who thought of a polar bear? Who thought of a brown bear, a black bear, a grizzly bear? What about Care Bear? What about a koala? People call those bears. This is why we want scientific names. We want to become more comfortable with them, at least be able to recognize them, because it'll tell us that's a unique thing that I'm looking at. Okay? So get familiar with it if you're not already familiar with it. So the Linnaeus system was great when it started, but it's changed. Linnaeus said you're either a plant or an animal. If you move, you're an animal. If you don't move, you're a plant. That worked for quite some time. But as our body and knowledge grew, we went from the earliest first system to the second system. This system, we started to develop 5 kingdoms, more organization. All right, you're in Kingdom Monera, basically all the prokaryotes. And then the Protista, the Plantae, the fungi, and the animals. Each kingdom had certain, let's call it admission requirements. To get into Kingdom Plantae, you had to have certain traits. To be in Kingdom Fungi, you had to have different traits or characteristics. And this worked well for a long time, for centuries. But then eventually, and this is back in the early 70s, this was proposed by a man named Carl Woese. He was in Champaign-Urbana, University of Illinois there. He proposed the 3-domain system back in the 70s, and it took about 25 years for it to really gain the traction and become firmly established. This is the system the majority of science uses. If you see any resource still talking about 5 kingdoms, ignore that resource. That resource is very old and outdated. Do not trust it. If it says, well, they're in Kingdom Monera, it tells you that's about 30 years old. Science has changed a lot in 30 years. So currently, we're on the 3-domain system. This is us right now. Bacteria, archaea, eukarya. Certain criteria. Once you're in a domain, you then drop down to kingdom, phylum, class, order, family, genus, species, and so on. Okay, so you start out in a domain, and you can do this bottom up, top down. It doesn't matter, whatever you're more comfortable with. But once you're in that domain, each domain will contain multiple kingdoms within it. So domain Eukarya has kingdom Animalia, Plantae, Fungi, and we'll talk about Protista. That's a hot mess. Once you're in a kingdom, there's multiple phylum within it. One of the phylum is phylum Chordata within kingdom Animalia. There's about 26 recognized phylum here in this kingdom. One we're going to reference right now is phylum Chordata. Within the Chordata, you then go to classes. There's class Mammalia. There's a whole bunch of different classes within Chordata. Once you're in a class, you then move to an order. Interesting, fun order to work with is Carnivora. There's also other orders. Notice all these little holes. These are all the different orders available within class Mammalia. If you are order Carnivora, you could then move to order Felidae. Right there, or right there, or right there, or right there. One of the many different orders, one of the many different families within the order Carnivora. So there's Felidae. If you chose to go to Felidae, then you could move to genus. Genus Panthera is one particular genus within the Felidae. There are other genuses, but the one we're talking about here is Panthera. Once you're in Panthera, you then move to species. If you're looking at this particular animal right here, Panthera pardus, the jaguar. Some people call him the leopard. Some people call him el tigre. All sorts of different common names. Scientific name is Panthera pardus. This is a very unique species of animal. So this is how we're going to run classification. I'll show you the train wreck, the hot mess of protists, talk a little bit about how that's working, but definitely make sure you are comfortable with this classification system. Okay? All right, now there is a change to the structure of evolutionary tree. People are thinking, and there's a lot of evidence supporting this, it's more of this bush formation. It's not this, here's a tree and everything branches up. Darwin proposed this visual hundreds of years ago. This is the thought. Here's your common ancestor. From that common ancestor, you get three groups branching off. One group went this way, evolved into the bacteria, oldest known organisms on Earth. The other group went this way, but then it split. One split went towards the archaea. The other split went towards the eukarya. So eukarya, believe it or not, are more related to the archaea. There's closer relatedness between these two groups because of traits than we would see between the archaea and the bacteria. And you would think, wait a minute, these guys should be closer to these, but they're not. They're actually closer to the domain that we fit in. So this is known as the bush of life idea, that it's more of a bushing appearance or bushing structure than a tree structure. Now, just to make you pull your hair out and aggravate you or maybe excite you, there's proposals about a ring of life. Is it possible ancestral species, common ancestor here, gives rise to the archaea that go this way, the bacteria that go this way, and then bacteria and archaea come together, literally symbiosis, to lead to the eukarya, that group right now. So that's the craziness that is being researched. So is it possible that eukaryotes rose as a fusion between a bacteria and an archaean? Oh,